So we're going to look at how the height of a drone changes over time. So the drone is depicted by this little triangle here in the lower left of the screen. And let's see what happens. Okay, the drone goes up into the air. It goes up some more, comes back down, goes up, and that was its path. Okay, so we want to look at this mathematically. We want to study this from a mathematical perspective. So what we're going to do is we're going to actually put time into the picture. So I've reset the drone to its starting position here. All right, so let's put time into this picture. So there we have t representing time. And we're also going to plot a point whose x-coordinate is the value of time and whose y-coordinate is the height of the drone. So let's put that point into here. Now let's let time evolve again and see what happens. Keep your eye on both the drone and also the point that we've just created. So we see that as the drone goes up, the point goes up. But the point is also moving to the right because time is moving forward. And as the drone goes down, the point goes down. And again, as the drone goes up, the point goes up. Now, if we look at the path that that point just traversed, that is giving us a graph. It's a graph of the function which gives the height of the drone versus time. And we can go ahead and plot that, and that's what it looks like. This is a graph of the height of the drone given as a function of time. Now we want to make some statements about this graph. What important features does it have? Well, we can see that when the drone's height is increasing, so if we let time evolve, you see the drone's height is going up. We see that the graph goes up from left to right. So when you see the graph go up from left to right, that means that the value that we're looking at is increasing. This next part, we see that the height of the drone is not changing. The height of the drone did not change, and that is represented by the graph being horizontal. This is also called a constant piece of the function. So when a function is constant, the value is not changing. When we get to this piece, we see the graph is going up from left to right again, and the height of the drone is increasing. Here, the graph is going down from left to right, and the height of the drone is decreasing. And again, we get to a part where the graph is going up from left to right, and the height of the drone is increasing. So we have two important features of graphs, where the graph is increasing and where the graph is decreasing. Here's another part where it's increasing. We have some other important points on this graph. We have the absolute minimum height of the drone, and that is depicted by this point down here. This is the lowest the drone ever was. This is the absolute minimum point. We also have an absolute maximum point. This is a point where the drone is at its absolute maximum height. Now there's actually two of these. Do you see the other one? Well, yeah, the other absolute maximum is over here. So this is an important point to make here, that the absolute maximum and absolute minimum, while there can be only one value, right? The height is the biggest here. There can only be one value for the absolute max or min, but it can occur at more than one point. So keep that in mind. It can occur at more than one point. We also have local maxes and local mins. A local max or local min is where the value that we're looking at is highest nearby, for all points nearby. And that's exactly what's going on here. If I just look by this point, the point is higher than it will be anywhere else nearby. Right? So if I wiggle the position of this point just a little bit, we can see it can only go lower. Right? So that's called a local maximum. We also see a local minimum over here, right there. Right? If I wiggle the point nearby, it can only get bigger. And so that makes that a local minimum. So we have local maxes and local mins, and we have absolute minimums and absolute maximums. Now, when we talk about maxes and mins, we want to know sometimes what is the maximum or minimum value, but we also sometimes want to know when does it occur or where does it occur. And so you have to be very careful about what you're thinking about or what you're being asked about. All right, so suppose we're asked about the absolute minimum of this function. Well, if we want to know what the absolute minimum value of the function is, we know that that occurs over here, right? Now, the value of the function is the height of the point. Well, the height of this point is 0, so we would say the absolute minimum value is 0. Where does it occur? Well, it occurs when x is 0. So in this case, they're both equal to 0. Now, what about the absolute maximum? Now, we said there are two absolute maximum points. There's one here, and there's also one over here. So if somebody asks what is the absolute maximum value of the height of the drone, well, it doesn't matter which point you look at because they both have the same value, right? They both have the same height. Either way, the answer is 10. However, if somebody asks when does the drone achieve its maximum height, well, now we have two different answers, right? We can say, well, the maximum height occurs here when x is 20, or after 20 seconds, but also the maximum height occurs here when x is 11, or after 11 seconds. So there's actually two answers. You can say the maximum height occurs at 11 seconds and also at 20 seconds. All right, next we're going to talk about average rate of change. So when something is changing over time, we can talk about how quickly it's changing over time. When you run, you can run quickly or you can run slowly. The rate at which you run is the speed that you're running. So this is something that's very interesting to us. We want to know how quickly something is changing. That way we can compare how something's changing in different ways at different times. All right, so how do we compute the average rate of change? Well, to compute the average rate of change, we need to find 2 points on the graph of the function. So here are 2 points. Let me actually grab this red one, move it over here. All right, so suppose I want to know the average rate at which the height is changing over the time interval from 0 to 10. All right, so what I'll do is I'll take this first point and put it at x equals 0, and the second point and put it at x equals 10. Can I get it exactly at 10? Well, I can get close. Come on, go to 10, go to 10. All right, well, there we are. All right, so I want to know what was the average rate at which the height was changing over this time interval. Well, when you think about how we measure speeds, we measure the distance traveled divided by the time it took to do it. Well, in this case, the distance is represented by the height, and the time is represented by the difference in the x values. So we're going to look at the ratio of the change in heights divided by the change in times. And that's exactly what we've done here. We've computed the difference in the y-coordinates of these points, y2 minus y1, the y-coordinate here minus the y-coordinate there, and divided by the difference in the x-coordinates, the x-coordinate of this point minus the x-coordinate of this point. And that's what we've written down here. And when you compute that, you get a number. That number is the average rate of change. Now this has a geometric interpretation. This represents the slope of this line segment, the line segment joining those 2 points. This is called the secant line, the line segment joining 2 points on a graph, the secant line. Now, if I want to know the average rate of change over the time interval from 4 to 7, let's go ahead and do that. So I'm going to put this point so that its x-coordinate is at 4, and I'm going to take this point and put it so its x-coordinate is at 7. All right, and we'll do the same computation. We take the change in y values, which in this case, where's my finger? Okay, in this case is the difference 8 minus 8 divided by the change in x values, 7 minus 4, and we get 0. So we see the average rate of change over that interval is 0. Well, that makes sense because that's when the drone was just hovering at a constant height. So the height's not changing, so it makes sense that the average rate of change would be 0. Now let's look at the average rate of change over the time interval from 11 to 16. So I'm going to take one point and situate it so that it's at x equals 11, and the other point at x equals 16, and we'll measure the average rate of change, the slope of this secant line. So I'm going to take the difference in the y values, so 2 minus 10, that's what I wrote in the numerator, divided by the difference in the x values, 16 minus 11, and compute that, we get negative 1.6. The slope of that line is negative 1.6, and that is the average rate of change. Note that it's negative. That means the height is decreasing on average over that time interval. Now, when the average rate of change is negative, does it always mean the height is always decreasing? Well, no. I see that if I look at the time interval from 6 to 16, we see that there are points in between where the height is increasing. What this is telling us is that on average, the height is decreasing. This is just an average. Now, I want to point out one very important thing here. When we do these computations, we have to be consistent in the order in which we subtract in the numerator and the denominator. What you should always do is pick one point to be point 1 and the other point to be point 2. So the coordinates of point 1 are x1, y1. The coordinates of point 2 are x2, y2. In the numerator, I did y2 minus y1, and so in the denominator, I did x2 minus x1. It would be incorrect if in the numerator I did y2 minus y1 and in the denominator I did x1 minus x2. I can't flip-flop. If you do that, you will get the wrong answer. So you have to be consistent. If you subtract with point 2 first in the numerator, point 2 should also be first in the denominator. Now, does it matter which point you call point 1 and point 2? Well, no, that doesn't matter. Watch. This number is negative 0.6. I can flip these 2 points. Let's put this blue point at 6 and the red point at 16. And you see, I get the same answer. All that matters is that I'm consistent in the numerator and denominator. If I do 2 minus 1 in the numerator, I have to do 2 minus 1 in the denominator. If I do 1 minus 2 in the numerator, I have to do 1 minus 2 in the denominator. As long as I'm consistent, I'll get the right value. It doesn't matter which point you choose to be point 1 and which point you need to be point 2. But we do need to be consistent. Whatever order you did it in the numerator, use that same order in the denominator.